With the rise in digital learning and online assignment submissions, plagiarism has become a significant issue in educational institutions. It not only challenges academic honesty but also undermines the efforts of genuine students. To address this, we need a dependable system that can accurately detect various forms of plagiarism. This study focuses on researching and evaluating different algorithms to determine how well they detect plagiarism. Our objectives are threefold, which is to examine major plagiarism detection techniques, to assess their accuracy, time and space efficiency, and finally, to identify the most effective algorithm or academic use.
Assalamualaikum and good afternoon. My name is Anis Nadia binti Muhammad Zamrin. Today I will be presenting on a set of 3 carefully selected algorithms used for plagiarism detection in academic settings. In this case study, we aim to address different types of plagiarism, from direct copying to paraphrasing and even camouflage reuse. After thorough evaluation, we choose the following 3 algorithms because they are highly complementary and suitable for a layered detection system. The first one is Rabin-Karp algorithm. We selected the Rabin-Karp algorithm primarily for its efficiency in detecting direct or near-direct copying. In many real-world cases, especially in source code or written assignments, students tend to copy content with only minor changes, such as switching variable names or changing word order slightly. For example, if 2 students write firewalls are essential in filtering traffic and another writes almost the same thing, so Rabin-Karp will catch the similarity quickly. So Rabin-Karp works by scanning text using a fixed size window and generating hash values for each substring. If a match is detected through identical hash values, the system performs a detailed comparison to confirm it. This approach allows for rapid scanning of large document sets with minimal memory usage. So what makes Rabin-Karp a strong first layer in our system is its speed and low computational cost. It allows us to filter out clearly plagiarized content before applying more resource-intensive techniques. While it doesn't handle paraphrasing well, we choose not to reject it because it offers an essential baseline capability that other semantic models lack. So the second one is TF-IDF with cosine similarity. Term frequency inverse document frequency. So our choice is TF-IDF combined with cosine similarity, which targets semantic plagiarism such as paraphrasing and synonym substitution. Unlike Rabin-Karp, this method doesn't rely on exact word matching. So instead, it evaluates the meaning and importance of words within documents. For instance, if a student writes the firewall protects the network from unauthorized access, and a student writes a firewall helps secure the network from outside access, the system will recognize the similar meaning even though the words are different. So TF-IDF assigns weight to words based on how frequently they appear in a document and how rare they are across all documents. This weights turn each document into a vector. So cosine similarity then calculates the angle between vectors to determine how closely 2 documents align in terms of content. If the angle between their vectors is small, the similarity score will be high. This algorithm is especially useful in essay-style writing, where students might change sentence structure or use synonyms to hide copying. It offers deeper insight into meaning, making it essential for assignments that test understanding rather than syntax. We chose this method despite its higher computational cost because it brings a semantic layer of detection, which is meaning-based similarities that Rabin-Karp and fingerprinting cannot achieve alone. Winnowing document fingerprint. Finally, we selected the third algorithm, which is winnowing algorithm, for its robust fingerprinting mechanism and proven use in tools like MOSS. It is particularly good at spotting camouflage plagiarism, where copied content is hidden within restructured or edited areas. So, winnowing begins with pre-processing and then breaks the text into kgrams, which is a small sequences of words. Each sequence is hashed and the lowest value in each sliding window is selected as a fingerprint. These fingerprints act as a signature of the document. If 2 documents share multiple fingerprints, the system flags them, even if punctuation, order, or formatting has been altered. This makes winnowing ideal for code plagiarism and large academic data sets. So its linear time and space complexity makes it scalable and accurate, even with minor surface changes. Unlike simpler exact match techniques, winnowing provides a noise-resistant method while still maintaining a high detection rate. That's why we did not reject it, despite the fact that it focuses on structural similarity rather than meaning, where it means it balances the overall system. So why these three? It is to ensure fairness and efficiency in plagiarism detection. We strategically combine these three algorithms. With the first one is rubbing cup detects exact copying quickly and efficiently. Second one, ATF IDF with cosine similarity finds paraphrase and semantically similar content. And the last one algorithm is winnowing uncovers hidden or structurally altered copying through fingerprinting. So together, they form a powerful layered approach that can detect plagiarism from basic copy-paste to advanced rewriting. This combination was not made arbitrarily. It reflects our critical analysis of the strengths and trade-off of each technique, ensuring we cover all possible types of plagiarism in a balanced and scalable way.
Hi, my name is Amir Husna, and I'll briefly explain three powerful algorithms used for plagiarism detection in academic setting, which are rubbing cup algorithm, TF-IDF with cosine similarity, and winnowing document fingerprinting. Let's start with rubbing cup algorithm. This algorithm uses a rolling hash technique to detect exact or nearly exact text. It's especially effective in technical reports like our datacom assignments, where students often copy-paste the same router or blend configurations. Because of its efficiency, O in brackets n plus m, in the average case, it can scan many documents quickly, which is perfect for large classes. It also has low memory usage, which makes it suitable for use on shared university servers or simple systems. However, RavenCup has a major limitation. It cannot detect paraphrase content, so if a student rewords a copied section, it won't be flagged. That's why it's usually used as a first level filter, especially for command line or configuration based plagiarism. Now, on the other side, we have TF-IDF combined with cosine similarity, which is designed to catch semantic similarity. In other words, plagiarism by paraphrasing. TF-IDF gives weight to terms that are important in one document but not frequent across all documents. Cosine similarity then measures how close two documents are in meaning even if they use different words. This method works best for content like justifications, conclusions, or theoretical sections in a report. The downside is that it's more computationally expensive and uses more memory due to the high dimensional vectors it generates. Also, it can sometimes give false positive if two documents share common technical vocabulary. For example, first we have the Rabbit Cup algorithm in action. Imagine two students submit their datacom reports. In the router configuration section, both of them include the exact same block of commands. For example, they both use interface gigabyte Ethernet 0/1 followed by encapsulation dot 1Q10 and then IP address 192.168.10.1, 255.255.255.0. Now, RabbitCup processes this by converting each line into a hash value and then slides a comparison window across both documents. Since the commands are exactly the same, they hash match perfectly. As a result, the system flags this block as potential plagiarism due to the exact match. The strength of RabbitCup here is that it can efficiently detect copied comments or configuration blocks even in very large documents. Now, let's move on to the second example using TF-IDF with cosine similarity. This time, the scenario is based on paraphrase content in a theoretical explanation. Group A writes, subnetting is used to divide a large network into smaller, manageable subnetworks to optimize routing efficiency and enhance security. Group B writes something quite different on the surface. The process of subnetting allows breaking down a big network into multiple smaller networks, improving routing and network security. Although the words are different, the core meaning is the same. Here's how the algorithm works. TF-IDF assigns weight to words like subnetting, network, security, and routing based on how important and unique they are across the documents. Then, cosine similarity calculates how close these two sentences are in vector space. In this case, the similarity score is very high. For example, above 0.85. So, the system flags this section as potential semantic plagiarism. The key strength of this method is that it can detect paraphrasing even if no exact words are copied.
Now, I will explain the winnowing algorithm, which is widely used in plagiarism detection, especially in programming assignment and technical reports. Its main purpose is to detect structural similarity, meaning it can cache content that has been copy-pasted or minimally edited, like changing spacing, punctuation, or adding a few extra words. Winnowing works best for source code, technical document, or reports where someone tried to discuss plagiarism using formatting tricks. In terms of performance, it is quite efficient. The time complexity is O, and to generate fingerprints where n is the number of characters. Then if we compare multiple documents, the total comparison time is O and squared time, F, where F is the number of fingerprints. Space complexity is also low in only store a few selected hashes instead of the whole document. However, winnowing cannot detect paraphrased content. It's only match exact or nearly exact sequences. So it is not suitable for detecting reworded text, but it is excellent at spotting copy blocks with minor edits. A good example of where this is used is MOSS, a system many universities rely on to detect code plagiarism. Even if a student changes variable names or add comments, we know it can still flag those similarities. So overall, it is a fast and practical tool for identifying obvious copying, especially in academic settings. Now, let me show you an example of how the winnowing algorithm works in practice. In this scenario, Group A and Group B wrote about the same networking setup, but Group B made some change. They add extra sentence and slightly change the structure of the original content from Group A. Even though the wording is a bit different, the main technical parts like the VLAN assignment and the rotor on state setup are still present. Winnowing handled this by first removing punctuation and converting everything to lowercase. Then it creates overlapping segments called kgram and extract fingerprints, which are basically hashes representing key parts of the text. When comparing the fingerprints of both groups, it still finds mesh in the core parts of the sentence. So even though Group B adds some fluff, the algorithm still detects the similarity and flags it for plagiarism. The strength of this method is that it can catch disguised copying even when the content is slightly edited.
Assalamualaikum and hi, I am Nadira who will present you the synthesis of findings for Rabin-Karp TF-IDF with cosine similarity and winnowing algorithms for plagiarism detection. In this session, we analyze the core characteristics and effectiveness of three key algorithms used for plagiarism detection: Rabin-Karp TF-IDF with cosine similarity and winnowing. Rabin-Karp uses a hashing technique that is highly efficient in locating exact or nearly exact matches. It works well for structured content like code snippets or templates tag. However, its sensitivity to word arrangement and high chance of hash collisions make it less suitable for paraphrase content. On the other hand, TF-IDF with cosine similarity excels at identifying content that shares the same ideas but is expressed using different words or sentence structures. It evaluates the semantic similarity between two texts, making it ideal for detecting rephrased or conceptually similar academic content. However, its computational cost is significantly higher due to the need to compare all word vectors. While on the other hand, winnowing applies a fingerprint method that is effective in identifying large copied sections, even if small changes have been made. It works by generating fingerprints from the text and comparing them to find structural similarities. While this method is efficient for detecting disguised or cosmetically altered content, it may not recognize subtle paraphrasing. When used individually, each algorithm addresses a specific aspect of plagiarism, but when combined, they provide more reliable and comprehensive detection across a wide range of plagiarism types, whether exact copying, paraphrasing, or disguised structuring. Now, let's move to the comparison based on the analysis for Rabin-Karp, TF-IDF with cosine similarity, and winnowing algorithm. A comparison table clearly outlines these differences to guide the selection of the right algorithm based on institutional or project needs. This part of the discussion presents a comparative analysis based on 5 criteria: similarity type, time and space complexity, reliability in detecting paraphrasing, sensitivity to word arrangement, and the ease of implementation. Starting with similarity type, Rabin-Karp detects exact matches. TF-IDF with cosine similarity captures semantic or conceptual similarities, and winnowing focuses on structural or paraphrase similarities. These highlight their different applications depending on the nature of the text. In terms of time complexity, Rabin-Karp is the most efficient with O n plus m, suitable for large datasets. TF-IDF with cosine similarity is more time-consuming due to its O and m complexity, as it calculates weights and angles between document vectors. Winnowing operates at O(n) per document, making it efficient for fingerprinting large volumes of text. Space complexity also varies. Rabin-Karp requires minimal extra space, while TF-IDF with cosine similarity needs more storage for document vectors. Winnowing, however, uses a small amount of space to store fingerprints. When evaluating paraphrasing detection, Rabin-Karp performed poorly due to its sensitivity to exact sequences. TF-IDF with cosine similarity and winnowing both show high effectiveness, although TF-IDF with cosine similarity better handles conceptual paraphrasing, and winnowing handles structural variation. Lastly, implementation complexity is lowest for Rabin-Karp. It's easy to apply but limited in capability. TF-IDF with cosine similarity and winnowing are moderately complex and require more understanding, especially when tuning them for academic environments. In educational institutions, plagiarism has become increasingly widespread. This not only affects academic integrity, but also reflects a decline in students' critical thinking and originality. To address this, universities require plagiarism detection systems that are both scalable and reliable to handle high volumes of submissions across various formats. RabbinCarb, due to its high speed and low resource usage, is highly efficient for scanning large sets of text for exact duplicates. It's especially useful during the initial screening phase or for reviewing structured content like source code. However, it lacks the ability to detect reworded or paraphrased material. Next is TF-IDF with cosine similarity. TF-IDF with cosine similarity is more suitable for in-depth analysis. It helps uncover paraphrased content, ensuring students don't simply replace sentences without original thought. This approach is essential in assignments that require individual interpretation, such as essays or theoretical discussions. Winnowing provides strong capabilities for processing large document sets. Its fingerprinting method helps to uncover copied content that may have been cosmetically altered. This is especially effective for code plagiarism or when student copies large portions of content and adjust sentence structures slightly. In practice, no single algorithm can cover all cases of plagiarism effectively. Therefore, a hybrid system that combines RabbinCarb for initial filtering, TF-IDF for semantic analysis, and winnowing for structural comparison is recommended. This layered strategy ensures a balance between speed and accuracy, maintaining both efficiency and academic standards in institutional environments.
In conclusion, we evaluated three key algorithms for plagiarism detections. The RabbinCarb method is highly efficient in identifying exact or near-exact matches, especially useful for programming or technical content. Meanwhile, TF-IDF cosine similarity is effective in recognizing paraphrased material in essay-style assignments, although it requires more computational power. And the last one, winnowing stands out for detecting structural similarities even when the content has been rearranged or formatted differently. Each algorithm addresses a specific form of plagiarism, so rather than relying on just one, we recommend a hybrid strategy that combines all three. This approach ensures both accuracy and efficiency, particularly valuable in academic settings with a wide range of student submissions. Thank you. That's all from me.